So, welcome to another lecture on time series analysis. And today we are going to cover the concept of stationarity and understand why it's important in time series modeling. Um, so, what we're going to cover is first defining what stationarity is, and then we'll explore why it matters. It doesn't always matter, but we'll explore why it matters in this case. We're also going to explore how to make non-stationary data stationary. Then we're going to learn how to test for stationarity, and I will introduce you to the concept of differencing. Let's go to the next one. So, what is stationarity? Stationarity is okay. Let's look from let's look at this definition from this book called Time Series Forecasting in Python. And I'd recommend anyone that wants to understand time series from first principles to read this book. So a stationary time series behaves roughly the same way over time. Its average, the amount of variation, and the relationship between nearby observations don't systematically change as time passes. Now that's a mouthful, but basically, a stationary dataset is a dataset that has the same mean and standard deviation over time. Yeah, standard deviation is just how far apart the points are from the central, the mean. Okay, let me just move to the next slide. So here we have a plot of an example of what a stationary dataset would look like. You see, as much as there are peaks and valleys, there's no trend. That's actually a better definition. A stationary dataset has no trend. It's constant. So as you can remember from the previous lecture, when we were doing time series decomposition, we had to divide the dataset into the trend, the seasonality, and the residuals. So that's why we do decomposition to remove the trend from the dataset and make it stationary so that we can model it using some algorithms in statistics that assume that the dataset is stationary before you start making predictions. So as you can see from this plot, a stationary dataset is stationary. It's not moving, right? It just goes up and down, but it's within the same level. So it has the same mean, which is the average level of a time series dataset, right? It's like from this dataset, we can see the mean is around 50 because there are points above and points below. So that's where the mean would be. The standard deviation is how far apart, how spread the data is from the mean. And the variance is just standard deviation squared. Or rather, the standard deviation is just the square root, the variance. So why does stationarity matter? Um, well, before we answer that question, let's look at these two plots. One is shows the variance for an unstationary dataset. It's always changing over time. And the other one is for the stationary dataset. You can see it's constant. And that's the same case for the mean. The mean for the non-stationary dataset is changing over time. And the mean for the stationary dataset is constant over time. So back to the question, why does stationarity matter? Well, the simple answer is that most statistical algorithms used in time series assume that the data being used on them is stationary. And I think the reason they do that is because it's easier to model data that is not changing as opposed to data that is changing. However, in this series, we will explore some methods such as using neural networks to predict data that don't require stationary. Yeah. But the models that we will first learn, which are ARIMA, SARIMA, SARIMAX, and VAR, all assume stationarity. But I'll show you a trick on how you can pass non-stationary data into these models and have them do the differencing themselves. Okay, now in this lecture, in this slide, this is the process of how we take an unstationary data set and make it stationary. First step is to load the data set. Then we test for stationarity, teach you how to do that. Step 3, if the data is stationary, we proceed to the next stage, which is modeling the data, predicting, doing all that fancy stuff that you're here to learn. And step 4 is if after differencing, the data is not stationary, which you have to test for stationarity again after differencing, which I'll teach you how to do. If it's not stationary, difference it a second time. That's called a second order differentiation. Don't worry about this. In the next 2 or 3 minutes, you'll understand this concept. And then finally, you use the difference data to make predictions. After you make the predictions, you have to integrate that difference in component back to the data set, because what we'll be predicting is the changes. I don't know if that makes sense. Let's just go to the next slide. Maybe it will be clearer there. So how do we test for stationarity? The most commonly used method is called the augmented Dick-Fuller test. And this method assumes that the data is non-stationary and will only show that a data is stationary if the Fuller statistic has a p-value that is below 5% or 0.05. In most statistical analysis, we always assume that for the null hypothesis to be flawed, to be disproven, the p-value has to be below 5%. And so that's what the ADF test does. In code, this is very simple. I just want you to have a high level understanding of this works. So the augmented Dick-Fuller test, it tests for unit root in a time series. What the heck is even a unit root? Let's assume that today's value is a product of some constant. Okay, let's say $3 plus yesterday, a proportion of yesterday's value and some noise, which is shown by this equation here, right? Like, let's say the stock price tomorrow for a stock that we're interested in will be $3 plus some value of today, let's say 0.5 of today, plus some noise, right? If the value of yesterday is weighted, it's weighted by coefficient alpha. If alpha is less than 1, then the data is stationary, which makes sense because it says if today's value is 0.5 of yesterday plus some constant and some noise, the data is not rising. But if alpha is greater than 1, it means every day, every subsequent day, the price is increasing from the previous day. So if today the stock price was 20, tomorrow would be, let's say 25, 23, C is 3, and the noise of the day after that would be 25 plus 3, 28, plus some noise, maybe 1, would be 29. So it would always be increasing and you would have a trend. So the augmented Dick-Fuller test just tests for a unit root. And a unit root is when the value of alpha, the weight of yesterday's value, is equal to 1 or greater than 1. If it's greater than 1, then the data is not stationary. If it's less than 1 but greater than 0, the data is stationary. If it's less than 1, the data is not stationary because now we have a decreasing trend. Okay, I know this is an abstract concept. When we get to the code, it's going to be much easier to understand. So yeah, let's go to the coding example. So these are the 2 data sets we're going to use. I'm going to put their links in the bio below. And yeah, let's get to it. First, let's import NumPy, pandas, and from stats models. I hope in the previous lecture you already install the stats models package if you're doing this on your computer, but on Colab it's already installed. We're going to import these libraries. It's taking its sweet time. Then we're going to read one of those data sets, the monthly mean temperature. We'll plot the first 10 elements using the dot-head method that you can see it. So it shows the monthly mean temperature from 1920 to around, I think it's around 1980. And we're going to plot these data sets. As you can see from this plot, this data set already looks like it's stationary. It's not that different. But anyway, we cannot assume that, so we have to test it. As I pointed out here, we are going to import the addFuller method from the stats models package. And here you just come in, let's plot it. Let's get it. Let's get the statistics. As you can see here, it says that the statistic, ADF statistic is -3, and the p-value is 0.01, so it's 1%, which means the p-value is below the threshold of 0.5%, meaning that this is a stationary data set, right? But this is not always the case. So as we saw in the previous slide, sometimes the data can be stationary out the gate, but that is not always the case. So the question is, what do we do when the data is not stationary? Okay, so now here's where I'm going to teach you the concept of differencing. Differencing is simply taking today's value and subtracting yesterday's value from it to remove the autocorrelation from the data set. Autocorrelation is when this time step is dependent on other time steps, right? So if we take yesterday's stock price and subtract it from today's stock price, what we'll get is the difference, right? The change between yesterday and today. So by differencing, by removing the impact of the previous day's value, the data set that we get is now just more likely to be stationary. I don't know if that makes sense, because we're just looking at the changes, not the whole thing. And what this means is that taking the current time step value and subtracting the previous time steps value from it to get the total value of both time steps and repeating this for all time steps in the data set. That is what differencing is. But the beauty of Python and NumPy is that we don't have to do this for every day, right? We don't have to write loops subtracting the previous day's value, because NumPy just helps us do that very easily. So let's get to the code example so that you can see how differencing works. So we're going to use the dataset that we used in the previous lecture, the CO2 one. Because it was increasing, you can see that it's not a stationary dataset. I'll provide the link below. So let's load the dataset first. I think I have to reload these packages first again. Let's give it some time. Okay, so we've loaded the packages. Let's load that dataset now. Let's plot it. We don't need to see the first 10 elements because we did that in the previous lecture. So as you can see from this plot, this dataset clearly has a trend. So it's always increasing. So the mean between 1959 and 1964 is very different from the mean between 1979 and 1984. So this is not a stationary data set, but we have to test it first. We cannot just use our eyes to make statistical predictions. So we call the add fuller method on the data set, the new data set. And as you can see, it has an ADF statistic of 2, positive 2, and it has a p-value of 1. That is 100%. And as we said before, for any statistic to be, for any measure to be statistically significant, the p-value has to be 5% or 0.05. So this data set is clearly not stationary. Let's use the traditional way of plotting it. And so we're just going to do diff dot plot. Yeah, as you can see from this plot, this data set looks more like the previous one. It's stationary, right? It has almost the same mean and same changes in value, which range from -2 to +2. So with this data set, just from looking at the data and how it's presented, we can tell that it's a stationary data set. But as I said before, we don't use our eyes to make statistical predictions, so let's call that Fuller method on it. And we're going to start from the second element because you cannot difference the first element because there's nothing to subtract from it. And voila, we have a p-value that is 0.0008, which is way below the 0.05 threshold, meaning that this data set has now been made stationary, and we can proceed to the next stage, which is using ARIMA to predict the data. And that is the lecture for today. So in the next video, we'll get into the ARIMA model and show you how it works now that we have the